Okay, a couple things I want to point out to you. We are having a new set of quotations of the day for the month of February. Dr. Martin Luther King Jr. And so every month I have a different person that I have quote of the day for. Also, you'll notice here that the topic number 2 is the inner planets. We're going to start working on that today and probably Thursday as well. There's an enormous amount of information about any single planet. So the amount of things that I could talk about a single planet, I could lecture, like Venus. I could lecture on Venus for an entire semester and still have plenty of stuff to talk about. So we're going to try to hit some stuff that I think is important, particularly Mars, and then we're going to turn to the outer planets. That means that we are now blazing our way through chapters 6, 7, 8, and 9. And you should consider that to be your reading assignment for the next week or two. Okay? And it's kind of cool. It's different levels. The chapter 6 is kind of like a little summary of each planet. And then the other chapters go into a little bit more depth. So that's what we're going to do. And we're going to start today with that. I have some news concerning the moon, and you may have heard over the weekend that there's some new developments in the theory of how the moon formed. We think that our moon formed as a result of the collision of Earth with a Mars-sized planet, which we've nicknamed Theia, and way back in the early history of the Earth, and that there was a glancing blow, and that the remains of the other planet, and it swept up a lot of the Earth's, molten rock and everything like that, and got all conglomerated and formed this little spherical object that we call the moon. And they recently made some new isotope comparisons, and that's why I'm talking about it right now. And we're going to do a little bit of viewing of some of the data. And what they did is they compared some moon rocks and some terrestrial rocks from volcanic type and igneous formations around the Earth, and then moon rocks from the Apollo mission, and actually one meteorite that has been captured on Earth that they've since determined was actually a little piece of the moon chipped off and floating through space until it landed here. And what they found is that they've done very, very careful analysis of the oxygen ratio, the oxygen isotope ratios, and they found that they're very, very close. And there's a journal article in Science that I'm going to link in the extra readings section of our web courses area. You will have some homework on this, but not tonight. There's another article, more of a news type article instead of a technical journal article. I'll give you both of them, and we'll actually look at a little piece of the technical journal article today. And there's probably a few other news sources around the internet that I will include. I've looked at several. And that will show up in the extra readings page in web courses, so you can make a note of that. And you'll be asked questions about it on homework, and then you'll have questions about it in class probably, and on exams. So it's coming, and today's the first day of looking at it. Now here's a a data plot that I want to go over with you. And this shows some delta 17 oxygen and some delta 18 oxygen for, as it says up here in the upper right, or excuse me, the upper left up here, for lunar and terrestrial samples. And and it says using a fractionation line with beta equal to 0.528. Now, I'm not going to go into too much about what beta means, except to say that that is a parameter that they used to simulate what they think happened in the collision. In other words, you might say, well, the prime factor in the collision between Theia and Earth was the angle of collision. Or you might say, well, we know the angle of collision is 45, but the main factor we don't know is the speed of collision. Were they really fast, 100 kilometers a second, or 1 kilometer a second, or some variation of that? Now, the factor called beta is a way for these jokers to encode that numerically, what they think the actual collision scenario was. And what they do is they do a simulation. How would two big rocks, basically, still really close to being molten lava from the early part of the solar system formation, how would they interact? And so that's the single number that they've used. And they did many dozens of simulations, and apparently that's the simulation level, beta equals 0.528, that is the closest, that describes the process that they think happened. Now, I'm not going to go into that too much, but just to tell you that it does have a physical meaning. All right, let's take a closer look. Oh, and by the way, San Carlos olivine. Go ahead and write that down, San Carlos olivine, in your notes. It's a geology term, but this is an astronomy class, right? But we want to know all about the moon. We want to know how the planets form, and the moon is a rock, therefore it's geological. Earth is geological. And so we have to sometimes use geological terms. San Carlos is a place in Arizona that I'm going to show you on the map in a minute. Olivine, O-L-I-V-I-N-E, is a very simple and abundant mineral in the crust of Earth and in the moon, and we've found it in Mars, and I believe they've probably found it and detected it on Venus, although I'd have to actually look that up. But olivine is a common igneous, or a common mineral, frequently found in, it's green. It's greenish color most of the time, and found in igneous formations. Now let's take a close-up look at this. Now, the bottom of this graph, this is the close-up. Look at that, delta 18 oxygen, SMOW, good old SMOW. And notice that the middle of their plot is about, 5.1 or so. And that's for this dot right here. That's San Carlos olivine. All right, and here's the 0 point on the right-hand scale, and 5.1 about for the center here, and then here's the 0.5280 line over here. It's kind of slanted. All right, now, so this is what I want you to think about. That there's a range of delta 18, but in this diagram, let's look at it a little bit more closely here. These little half-moon icons, those are the Apollo moon rocks, and then the one lunar meteorite. And they are pretty close to all these items over here that are terrestrial, except for this one. That is way down in South Africa, the Bushveld Complex. That's this item here. So that's kind of an outlier. These plus signs, that is Gore Mountain Garnet. So that's from a volcanic formation or an igneous formation in upstate New York. I'll show you where that is. And then you can look at all these other data. Mauna Loa, that's Hawaii. Everybody knows where that is. SC, that's San Carlos in Arizona. I don't see any plus. Okay, here's San Carlos over here. And Olivine is, see all the circles, the white circles with the black edge? That's all different samples of olivine from the San Carlos Formation in Arizona. And what you can see here is there's stuff outside down here from South Africa. There's stuff over here from the San Carlos Formation. And the lunar stuff is kind of in between there. So what they're saying is that this collision mixed the oxygen isotopes and mixed them thoroughly between Earth and this Theia impactor, about the size of Mars, they think. And that is why they are so close together. So if we'd seen something that was way outside here, you know, this is a relatively small range of SMOW here. This is the delta 18 part of SMOW. Okay, delta 17 is over here. You know, there's much higher and much lower values of delta 18. But this stuff, it's looking good. And it's all igneous rock. These are igneous rock formations. There's no sedimentary rock on the moon. I mean, there's dust, there's soil on the moon, but it's because of, you know, constantly getting slammed by asteroids and comets and stuff, and blowing all those, you know, rocks into smithereens, and then eventually they settle back down to the surface of the moon and form a soil. But you know, they don't have sedimentary rocks like we do, you know, like sandstone or limestone. They don't have that on the moon. So it's all igneous up on the moon. And now, see this one? This half moon and this half moon both say lunar. Basalt. Basalt is the terrestrial name for a dark igneous rock, like the dark igneous rock out in Hawaii. You know, those black beaches in Hawaii are from dark rock that eroded and formed beaches on some parts of Hawaii. And those are, let's see, Mauna Loa. See, look at this. These triangles. The triangles are Hawaii. And see, the lunar stuff is very close to the Hawaiian stuff, so it's kind of cool. All right, now here's a picture. You could jot this down. Where's the San Carlos Formation in Arizona? And this is kind of we're taking a tour of the entire planet here. So first location, San Carlos, Arizona. There's Phoenix. Here's here's the actual location of the lava fields and the volcanic formations. And here's a little town of San Carlos. And here's the actual location where they took those rocks approximately. This is from Google Maps. So it's just, you know, go to Phoenix and then go east a little bit, kind of cut through the mountains here and over here by this big reservoir. And then down here, well, you can't see it, but down here off the bottom of the picture would be Tucson. And up here would be Flagstaff, up at the Grand Canyon's up there somewhere. Okay, so that's the San Carlos Formation in Arizona, east of Phoenix. All right, next notes. The Gore Mountain Complex. All right, now take a look at this. Now you can't draw a map of this, but you can make a note. Gore Mountain, igneous formation, upstate New York. It is north of Albany, New York. Here's Albany. the capital of New York. New York City is way down here by the bottom of by the floor. Okay, the Hudson River is kind of going down this way. Now, here's Montreal up here. Okay, so if you've ever been to Montreal, that's up here. And then over here is Buffalo. And then over here is Toronto. So that's a little, and this is Gore. This is the Gore Mountain Complex. So from one corner of the United States all the way to the other corner of the United States, and the rocks in those locations have very similar oxygen isotopes to those pieces of the moon that we brought back from the Apollo by the Apollo astronauts. So that's nice. Now check this out. Here's the Bushveld Complex. Oh, all the way down in the southern hemisphere on a different continent. It's right down here in the tip of South Africa. All right? And the kind of cool thing is, here's like a side view of the Bushveld Complex. It's kind of this big layer of igneous rock. And it's supposed to be one of the richest ore-containing bodies in the world for stuff like platinum and other kind of really expensive metals, really good metals. The other kind of cool thing is, right next to that and related to it is the famous Kimberley diamond mine in South Africa, just a few kilometers away from there. That's what they call a pipe filled with diamonds, and that's where a huge number of diamonds are mined. You know, it's big, and they haven't even gotten close to the bottom of that pipe. So, but they keep working on it. Anyway, so that's the Bushveld Complex. So these rocks, so here's your bottom line, your wisdom about this particular set of locations. 3 enormously distant locations, oxygen isotopes, similar to another really distant location, the moon. All those lunar rock formations on the moon. So yeah, we think that the moon and the Earth were in contact. Their oxygen isotopes mixed in some kind of a dynamical process. We kind of are trying to figure that out. That's what that beta factor is about. So we've correlated all that stuff to the Apollo. So go ahead and write down Apollo 12, Apollo 15, Apollo 17, and one lunar meteorite that they analyzed for this. And I'll try to dig up some more information on their machine. What they have is basically like a Calutron, an isotope separator like the Calutron that we've got, or that we discussed last week. And the Calutron has a magnetic field, and the lighter isotopes curve around a little bit more quickly, and the bigger isotopes a little bit more slowly, a bigger circle, and so they separate. And they analyze how many have they got of each isotope once they've separated them, and they can get a good estimate of, delta 18 and delta 17 oxygen. So, now questions on that before we continue? All right, we're going to do some clicking in a few minutes, so have your clickers ready. And we're going to start talking about some planetary concepts from Chapter 7. Here's a lovely image of Mars. What's your last name again? Clark? Okay, here you go. All right. First look at the terrestrial planets. Now, if you read Chapter 6, you learned about the frost line. And that is the imaginary boundary line between the terrestrial planets and the Jovian planets, or the gas giant planets. The inner planets tend to be rocky and metallic, and the outer planets tend to be gas, mainly hydrogen, and hydrogen-containing compounds. Right, so you can read about that on page 157. This diagram of the frost line, it means that inside the frost line, the only thing that can solidify are things like metals and rocks, because they have to be really hot to melt, but they don't have to be really hot to solidify. In other words, if you saw a lava flow in Hawaii, even though the lava is solidified, you could still feel the heat from it. You could walk on it if you have the proper shoes, but having the proper shoes means having heat-proof shoes because it's still really hot. And so outside of that frost line, that imaginary boundary in the solar system, stuff that's more volatile can start to condense, like water and like CO2 and even hydrogen. And when that happens, you get the gas giant planets. Now, we're going to be inside the frost line for the terrestrial planets. So think of it like the two different parts of a room. The hot part of the room is close to the sun, and that's where the terrestrial planets and only those. But if you move further away from the hot part of the room, you can still have ice cubes. You can make ice cubes there, and they'll stick around. It's not too hot to melt them. But in close, yeah, you're not going to have any, CO2 ice. Here's another thing that you could add to this analogy, and that is, so this is like D, item 2D for delta. Comets orbit far away from the sun, and some of them come in really close to the sun. Only when they get close enough inside the frost line do they start blazing out and evaporating out and catching all the sunlight that makes them visible. They reflect sunlight from the sun to us, but until they've passed the frost line and started to heat up significantly and outgas all those CO2 and H2O vapors, they won't really reflect much sunlight. Okay, they're just kind of nuggets, not very big. I mean, you can see them out there. They will reflect light as frozen nuggets, but it's very tough to see, unless you know where you're looking. And that's why it's kind of hard to find a comet until it gets in rather close. So the frost line is approximately between the orbit of Mars and the orbit of Jupiter. Okay, so Mars is at about 1.52 astronomical units. That's about 750 light seconds. I don't know, what did I have last time? We had a list of the size of Mars's orbit. Should be 700 or something light seconds. Jupiter's way out there, 5.2. And so the frost line, it's not like, some ultra precise location. And it has probably changed location according to the luminosity of the sun. The sun hasn't always been as bright as it is now. And it might have been brighter in the past or less bright in the past. And so the frost line would move in or move out accordingly. And so that's a key concept for understanding the entire solar system because it affects comets, meteorites, the asteroid belt, the terrestrial planets, their composition versus the composition of these gigantic outer planets, which they are gigantic. They're really big. So let's talk about Mars. This is the I mean, everybody can learn about Earth. I mean, there's a lot to learn about Earth. You know, volcanoes on Earth and all that kind of stuff. It's kind of cool. But Mars is the one that everybody wants to know about because we want to know about it. When we get some astronauts up there, can we make a hospitable abode for the astronauts? Or is it going to be impossible? You know, like the moon that is close, we could have a moon base, but there's hardly any water on the moon. The only place that there's water on the moon, we think, are up by the north and the south pole in the few craters near the North Pole and a few craters near the South Pole of the moon that don't get any sunlight because they're up there by the North Pole. You know, so no matter what time of its orbit, what part of its orbit around the Earth, there's shadows in craters of the moon near the North Pole of the moon that never get any sun. And in those shadows, we think, or we know, that there is frozen water. But everything else is evaporated out because the moon gets pretty intense sunlight. The sun is pretty intense. We're protected by the atmosphere. But if you were to go outside of our atmosphere like an astronaut, you've got to have really good protection from solar radiation. Same thing on the moon. So solar radiation is like a zapper. It zaps everything from the surface of the moon except for rocks. But as you can see from this picture, not Mars. Mars has got an atmosphere. It's colder. It's got a longer year. Its day is just about the same as ours, a little bit longer. And they've timed it. It's 24.6597 hours. Not like you'll have to memorize that. But yeah, it's a bit. So what you want to remember is a little bit longer. You know, 0.6597, 0.66. That's about 30 minutes and change. So it's got a little bit longer of a day. The axis tilt. Our axis, the axis of Earth, you know, like the imaginary axis that, you know, like a classroom globe that you can spin. It's got a little axle built through the middle of it. And that axle allows it to spin on its axis. And if it were the real planet Earth, that axle would point straight at the North Star. Now, Mars is a little bit tilted away from that, but not too far. It's pretty close to the North Star. So the North Star of Mars would be some other star, not Polaris, not our North Star. You know, their spin axis is pointing a little bit off from that. Its orbit is fairly eccentric, as we have discussed. And what that has as an implication is pretty important. Really important. And that is that there is significant annual variation in the length of the seasons. So for us, our spring, our summer, our fall, our winter are pretty much the same length because we are pretty close to a circular orbit. And it doesn't matter southern hemisphere winter and northern hemisphere winter, they're both about the same length. Now, the weather's not the same because the southern hemisphere has different weather patterns than the northern hemisphere. They got a lot more ocean in the southern hemisphere compared to up here in the northern hemisphere. We have a lot more continental landmass. But, you know, minute for minute, yeah, we have the same amount of winter. But not on Mars. In other words, southern hemisphere summer is different length than northern hemisphere summer. Let me repeat that. On Mars, the southern hemisphere summer is different length than northern hemisphere summer. Okay? Here on Earth, pretty much the same. On Mars, not the same. Also, Mars is closer during the southern hemisphere summer. But on Earth, we're a little bit closer, and we can measure it, but not as drastically closer as Mars is. So Mars, you get a lot of variations, okay? And what results from that is more extreme seasons. So you get some weather on Mars. They haven't got jack for an atmosphere there. Very thin atmosphere, very low atmospheric pressure. Okay, for us, we would croak if we tried to walk around on the surface of Mars, because there's no oxygen for us anymore for us to breathe on Mars, but there's a lot of CO2. But it's very thin, it's very sparse, very low atmospheric pressure. The temperature in the middle of the summer is not too bad. It would be like a cold day here in Orlando. You could walk around in maybe a sweater or something like that and survive, but the atmosphere is not as conducive. Here's what I mean about extreme seasons. Check this out. Okay, this is a very famous set of pictures here. 2001, so this is about 14 years ago. June 26, 2001, before the dust storm. And that's like a global dust storm. What? No, we get a dust storm, a little bit of the Sahara gets a dust storm. Arizona, a few square miles, might get a dust storm. You know, Oklahoma, the Dust Bowl. And they get some big dust storms over in the Gobi Desert, and they get some big ones in the Sahara. And they'll keep going. Those clouds of dust will come across the ocean and impact the North American continent. You know, when I lived in Montana, we would occasionally get these dust storms from the Gobi Desert come, and you know, astronomers were always sensitive to it because it affects how your telescopes can see, unless you're way high up in 10,000 feet or something like that. And we could see these just like a reddish patch floating across the North Pacific. Same thing down here in Florida. Did you guys ever notice that when we get the remains of a dust storm over here in Florida? Raise your hand if you've ever noticed that. Yeah. If you live in the Caribbean, which is about, like St. Thomas, the Virgin Islands, it's about 1,000 miles east of us. Here, you see it even more. It's like the whole sky is almost like it's sparkly. And when you see conditions like that, you think, ooh, dust storm. Dust storm 2 weeks ago in Libya. And now we're getting and they've measured that dust. I mean, there are rock formations in St. Thomas in the Caribbean where, they can measure that. They've analyzed the rock and they know, oh, this came from the Sahara. Because the Sahara has a very definite set of isotopic ratios. So we know where a lot of this stuff comes from. And if it comes from the other side of the Atlantic, we want to know all about that. But think about this. Those are little dust storms compared to this. I mean, Mars is a lot smaller than Earth. But nothing on Earth is the size of as big as this. That is a monster dust storm. 757 light seconds from its star. All right, let's take a look at some more of the basic specs. Here's Curiosity in 2012. One of the better. Those rovers they got up there. Oh, man. Okay, the equator, 13,000 miles if you were to walk around it. 24,000 here on Earth. And you could walk around the equator of Mars because there's no oceans. Here you can't. You could walk and row a boat around the equator or sail a boat along the equator of Earth and then get out and row. But on Mars, you could walk the entire equator. Subsurface water, yeah, we can see it, no problem. And go ahead and make a note of this ground-penetrating radar. We put a spacecraft up there in Mars, the Mars Express. It's kind of an amusing story. You know, they can see all kinds of stuff under the ground. They're looking for water. That's what everything about Mars is. We're looking for water. And why is that? Because we want to live there maybe someday. Or we want to at least think about living there someday. You know, someday, you know. And in the 1960s, back in the bad old days of the Cold War, the United States and the Soviet Union were negotiating missile treaties, right? You know, they wanted to limit the amount of destruction that they could pound onto each other and all that kind of stuff. So, you know, they were trying to get the Russians, okay, you guys reduce your missiles by 100, and we'll reduce our missiles, our land missiles by 80, and our submarine missiles by 20, or, you know, something like that. And so the question was, you know, how can we verify what the Russians say that they're going to do? All right, so there's ways to do that. And what they developed was a satellite in space that had ground-penetrating radar. See, this Mars Express has only been up there for a decade or so, right? But we've had satellites like that orbiting Earth looking down at the Russians since the 60s. Because we want to know what they got in their silos, in their ever-loving missile silos. And we could see every cotton-picking thing that they try to hide. And the way that we did that was they wanted to tell the Russians, yeah, you better make an agreement and keep it, because we're going to know it if you don't keep it. And here's how they told the Russians that basic message. They published in National Geographic a study of the Nile River Delta. And they showed all kinds of underground water courses and structures that the ancient Egyptians had built, you know, thousands of years ago, that were now buried by sand in the area of the Nile Delta. So around Cairo and, you know, the Great Pyramids and all that area, right? So they published all this stuff, and they were basically telling the Russians, yeah, this is for Egypt. They don't have any missile silos. But if we can see this in Egypt from space, we can see whatever you got over there in Siberia that you're trying to fib about, and we got it, baby. So that they couldn't tell the Russians what they had, but they told them what they had. And so they got the Russians to be honest for once. Any Russians in here? Okay. I mean, sometimes we have students from another country, and it's the Russians from 50 years ago that we're talking about, really. All right. Anyways, so ground-penetrating radar on Mars. Yeah, we know all about it. So if there's any alien structures on Mars, we know about them, and so far nothing. You know, we haven't. No missile complexes left over from the days of Jules Verne, no space alien pyramids, nothing cool. It's just kind of this planet. A third of the carbon dioxide in the atmosphere moves seasonally between the North and the South Pole. So what that means is, in the northern hemisphere summer, it evaporates. It goes from from dry ice at the polar ice cap in the north up into the atmosphere, and then the atmosphere, you know, the weather and stuff, mixes that stuff, and a lot of it that ends up near the South Pole then freezes, and freezes as dry ice, and crystallizes into dry ice down at the southern pole, and vice versa, you know, from south to north. So apparently they're able to track that. Another thing that Curiosity has found is many signs of possible life. And here's the other thing that they're really looking for. I mean, Everybody wants to know about water. I see your question. Hold on a second. But the other thing is there anything actually alive up there? And so they're looking for organic compounds. That means stuff. They're looking for carbohydrates, carbos. They're looking for carbo loading. They're looking for lettuce, grass, any kind of a vegetable would be a hydrocarbon complex carbon molecule. Methane, that's a kind of a gas. It's part of natural gas here on Earth. And so we want to analyze as much as we can from all those babies. Question over here.
Yeah, let's say that we do end up sending astronauts on Mars and that they do find water and signs of life. Is it possible to even create an environment where it's habitable for people?
Okay, the question was, for those of you that didn't hear that, what if the astronauts do find water and signs of life? Is it am I getting this right? Is it possible for them to create a habitable system there on? We think probably, and we know that there's water. There's no doubt about there being a lot of water. It's just not on the surface, and it's not liquid, not usually liquid. We've seen the signs of flowing water, and I think recently they filmed, they imaged some flowing water. I think just the last year or so. It's hard to find because there's not much of it, and we see the remains of the flowing water, but we haven't caught until just recently. I think they haven't actually caught flowing water, but we know there's water up there, and the answer is yes. We think we can do something. Because it's like it. You know what it's like? It's like if you look at the pictures of like this, that looks like parts of Montana. And I'm sure there's I don't know Arizona and New Mexico very well, but I'm sure there's parts of Nevada, Arizona, and New Mexico that look just like that. There's a place in Denver called Red Rocks. It's like a concert venue. All right. So, yeah, we think that eventually, if they do things right, that if we can get some guys up there and a little bit of energy and a little bit of tools and some food and stuff, yeah, maybe they can make a habitable, biosphere of some kind. But now there's this famous movie with Arnold in it, Total Recall. And in Total Recall, he's like this guy from Earth that gets sent to Mars. He's exiled he's sent to Mars. And he rescues some pretty girl, of course. That's how it's a movie. And in the process of that, they light off some nuclear detonation or some kind of explosion in this big volcano on Mars. And because they do that, they release a lot of water and oxygen into the atmosphere. And suddenly Mars becomes like this Garden of Eden. And so that's like an enormous fairy tale. It's a movie. And that part of it is a fairy tale. That's never going to happen on Mars, at least not that way. I mean, we may figure out some way of doing that. That's called terraforming, forming an Earth-like environment. We may eventually be able to do that, but that would be an enormous project. It won't happen like in that movie anyways. But theoretically, we think, yeah, that there's a possibility, at least forming small terrariums, small biospheres, we think. Yeah. So that movie, The Martian, raise your hand if you saw that movie, The Martian. I haven't seen it yet. Is it any good or does it suck? It's good? Because I saw in there that he was like growing plants or something in the soil. So that they can probably do that, but they'd need a lot of nitrogen to do that. It's just like in Israel. You go to Israel, that's like the desert, right? The Negev desert, but they get stuff to grow in the desert because they have water, and then they fertilize. And Think about anything growing in your yard here in Florida. What's the soil like in almost every part of Florida? Sand. And yet stuff grows here because we got abundant water and we got a little bit of surface vegetation, so we get some organic matter into the earth. But, I've always been amazed that anything grows in Florida because it's all sand. But except for like the river bottom, the swamps and stuff like that. But it's amazing. So, yeah, so we could, if we could get some people up there, it'll take a lot more effort than these movies, but, we could do it, we think. And the moon, dicey. Mars, tough, but probably doable if we wanted to. Another question. But what would happen if we did find, some subsurface structure? Boy, that would be kind of creepy. That would, like even if we found a single road, a straight road, one, so buried underneath the ground. Boy, and we'll talk about Mars here. Let's keep going. There's stuff to talk about with Mars that we used to think was sign of civilization. Not this though. Olympus Mons, the biggest volcano in the solar system, we think. Now, this is the state of Arizona. Look at that. Look at that outline. We don't have anything like that on Earth. Not even close. I think the biggest ones we have on Earth are the Hawaiian Islands. That's a series of volcanoes. This is one volcano. So this thing is 26 kilometers in height, 26 kilometers. So that's about 15 miles high. It's pretty big piece of mountain. And we don't even have one mountain here we got Mount Dora, but that's not really much, especially not compared to Olympus Mons, Mount Olympus. We've never seen it erupt, but we know, a geologist can look at that and say, even if he doesn't know what planet it's on, if somebody tells him, yeah, this is this place in Antarctica, he'll say, oh yeah, that's a volcano in Antarctica. You could try to deceive the geologist about where it is, but you couldn't deceive a geologist about what it is. That is a volcano, no doubt about it. We've never seen it blow, but we know that it could. And if we're going to look at the crater here of it in a second. So that's the state of Arizona, right? Now here's the state of Arizona from Google Maps, and the biggest system that we've got, I think, is the Hawaiian Islands. And so here's the Hawaiian Islands, this chain of islands. Here's the big island down here, the big island of Hawaii. Here's Honolulu, Oahu, and this whole chain of islands. That's pretty big. And they say that the Hawaiian Islands are actually bigger than Mount Everest if you count from the very bottom of the sea to the top of the volcanoes in Hawaii. They're bigger than Mount Everest. So that's it. So Mars is a smaller planet, but volcano-wise, we can't really compete. Hawaii's doing all right, but other than that, our volcanoes are pretty pathetic. Now let's talk about the atmosphere. Here's good old 7034, NWA 7034. Okay. The atmosphere of Mars is a distinctive mixture. 96% CO2, carbon dioxide, 3% nitrogen, trace amount of water vapor. Okay? The reason there's any water on Mars is because it's frozen. All right? We can analyze the rocks and so forth on Mars and the form, the erosion patterns on Mars. And again, a geologist cannot be deceived about that. They recognize the signs of flowing water. It's not easy to disguise. And we can see that. Okay, there are erosion features. There are melted water features. In other words, places where the ice is melted and the earth is caved in a little bit. We found rocks that on Earth form in water. So, and we found the same kind of rock formations on Mars. So we think, okay, this looks like it formed in water, flowing water, but not recently, because there's no flowing water, no abundant flowing water on Mars. There's a lot of H2O frozen in the polar ice caps. And so, you know, it's an interesting environment. When we talk about Venus on Thursday, we're going to have a vastly different environment, vastly different planet. It's larger than Mars. It's closer to the sun than Mars is. It's smaller than Earth, a little bit smaller than Earth, but vastly different. So it's an interesting situation. Now I want to talk about methane as well. So to talk about methane, we need to talk about the solar energy budget. And the solar energy budget affects the atmosphere. And what do I mean by that? Well, for Earth, if you were to take a solar panel 1 meter across and 1 meter tall up above the atmosphere, so a little bit further out than the space shuttle and the space station, because they're technically still at a very, very thin part of the atmosphere, I think, at that altitude. If you took a solar panel, you'd get 1,367 watts out of it. I mean, if it was a perfectly efficient solar panel. So if all the sunlight that fell on that solar panel, 1 meter across, 1 meter tall, if all that solar energy were converted to electricity, it would run like maybe a blow dryer. You know, so if you go home and look at a blow dryer, it's going to be in the area of 1,200 to 1,500 watts. Anybody know the wattage rating on the blow dryer at your house? Anybody have a blow dryer? I don't obviously have a blow dryer. Nobody has a blow dryer? Nobody wants to admit having a blow dryer? Does anybody? One person admits having, 2 people. Okay, good. They do exist, blow dryers. And so this is a typical wattage range for a blow dryer. Now, that means that every square meter of Earth facing the sun, I mean, if it was a perfectly clear day, most of that 1,367 would reach the Earth. But if it's a cloudy day, then some of it gets reflected. And the atmosphere itself, even if it's a clear day, will reflect a little bit of the sunlight back into space. But roughly, that's the amount of solar energy hitting every square meter. And we've got an enormous amount of real estate facing the sun every minute of every day. Now, right now, Orlando's facing toward the sun. It's the middle of the afternoon now, so we're about to go into the night side away from the sun, but we're still getting plenty of watts per square meter. Now, Mars, not even half. It's further away. So square meter for square meter, it's not going to get even half of what Earth gets. Because the solar energy, it still gets the same photons, but now they're spread out. You know, because they start from the sun and they just keep spreading out, you know, all through space. And if it happens to land on a planet, you'll get some watts per square meter. Now, Mars gets 591. Now, you could run, a cell phone runs on like less than a watt. Computer, probably a few watts. A laptop. 591 watts. That'd be like a mini blow dryer or a blow dryer that's, been amputated. I don't know. Oh, you know what else goes at about 1,000 or 2,000 watts is microwave ovens, smaller microwave ovens. I'm going to have to look up something that's 591 watts. 591 watts, that's like 10 60-watt bulbs of the old incandescent kind. So that's what the amount of solar energy blazing down to the surface of Mars. Now, Mars has a much thinner atmosphere, and so most of that energy hits the surface. All right? It heats up the atmosphere, and because that is the case, the gases in the atmosphere heat up. When gases get hotter, the molecules zip around on average much more rapidly. And if they zip around fast enough, if the temperature's hot enough, they'll zip around fast enough that they have escape velocity. And Mars is a smaller planet. So it doesn't have nearly the escape velocity that Earth does. In fact, it'll be easier to launch a spacecraft back to Earth from Mars than from Earth to anywhere. I mean, it takes an enormous amount of rocket. Anybody, raise your hand if you've ever seen the space shuttle take off or anything from Kennedy Space Center. So those things are blazing. They eat up an enormous amount of rocket fuel. They got those big monster boosters. Now, those things putting out a lot of watts per second, or a lot of watts per square meter. But you won't need that to get back from Mars. You need some, but not nearly as much. So here's what Mars does with it. So, and any planet really. Some of it will be reflected, and that tends to cool. Some of it will be absorbed, and that tends to heat things up. Whether it's a rock or whether it's a cubic meter of atmospheric gases, or anything else. Your left earlobe, if you're up there on Mars. Some of the light, the solar energy will be scattered. The photons of sunlight will be scattered. Kind of like here on Earth. We have a blue sky because of the way that blue light scatters in the atmosphere of Earth. Methane does the same thing. So here's a diagram of what we were just talking about. Okay, so here's Earth, and here's Mars over here. All right. So here's a little circular disk facing the sun. All right, and here's another circular disk, the same diameter as Mars, but facing the sun. And so this circular disk here by the Earth is the same diameter. I made it out of an ellipse, but it's supposed to indicate, kind of a perspective view of a circular disk. Okay, so here's the sunlight blazing in on that circular disk. 1,367 watts per every square meter of that disk. Now, some of that light goes blazing past and hits above the atmosphere of Mars. And here's its disk. Okay, and by this distance, it's diluted down. So use that word diluted. The solar energy is diluted because it's spread out over a bigger sphere. The sun blazes out its energy into all directions pretty uniformly. There's sunspots and stuff that don't blaze out quite as much, but it's pretty, the sun is pretty hot no matter what direction you're looking at it from. Okay? So, but in the plane of the solar system, a lot of it is absorbed by each planet. But the further out it has to go, the more territory that all that energy covers. And so by the time it's out there to Mars's orbit, you're down to 591, which is, it's okay. Here's another thing that this affects. You have a solar cell, solar power, solar energy panels. Like up on the space station, they got these ginormous solar energy panels up there, big ones. And they would not put out nearly as much power if they were orbiting Mars, because there's not that much energy per square meter per second on Mars. It's only 591 versus what we have, 1367. So you could have those lovely solar energy panels from the space station out there on Mars. They're still not going to pick up as much. You won't be able to run all your entire space station 24/7 the way we can here in Earth orbit, simply because it's 1.5 AUs out there. Question?
Do you know the size of that hypothetical surface is for Earth or for Mars?
Do I know what?
Like the size of the disk.
Yeah, pi r squared. Pi r squared. R for Earth is 6,371 kilometers. Actually, I think I've got that over here. Here's a data table. You can start jotting this down. Whoa. Lost my mic. Let's see. Here's radius. Yeah. So this should be 6,371. Earth's not a perfect sphere, so I must have put in the equatorial radius here. The average radius of Earth is 6,371. Anyways, here it is. So this is your radius, 3,397,000 meters squared times 3.14. And that would be the area of that imaginary disk, to catch all of the sunlight, heading for Mars. So, okay. Let's take a look at these specs. Mars, and here's the ratio with Earth. Okay, so the mass of Mars, this is scientific notation, 10 to the 23, that means 10 times 10 times 10 times 10, 23 times, times 6.42, and this one's times 10 to the 24. This rounds off to 6. This one rounds off to 6. So the ratio here is pretty close to 1 to 10. In other words, for every gram of mass that Mars has, Earth has got almost 10. Earth's got 9.3 grams because it's a bigger planet. Radius. Okay, now this one rounds off to 3.4, 3,400 kilometers. This one, 6,400 kilometers it rounds off to. So you're talking almost 2 to 1 or 1 to 2, and there's the ratio. For every kilometer of radius on Mars, Earth's got 1.88 kilometers. Right? So it's almost double the radius. But what that means is that the surface area of Earth is almost 4 times the surface area, because the area of a sphere is 4 times pi times r squared. You better write that down. Surface area of a sphere, formula, A equals 4 pi r squared. I'll try to remember that for the next class. Area of any sphere, 4 pi r squared. The volume of a sphere, better write this one down. Volume, capital V, 4/3 times pi times r to the 3rd power. So if the ratio is 1 to 2 for radius, it's 1 to 4 for surface area, and it's 1 to 8 for volume. So Earth's volume is almost 8 times the volume. Now this factor here, m over r squared I'll have to explain that next time. Here's the surface gravity. This is our free fall acceleration, 9.8 meters per second squared. That's how many extra feet per second of speed you get for every second of free fall downward. On the moon, it's only 3.71. On Mars, it's 3.71. On the moon, it's like 1.6. It's very weak on the moon. Here's the orbital diameters. And this is the astronomical unit here, 1.524 to 1. And then C, this is the solar, this is called the solar constant, capital C. And you can see that for Mars, for every 1 watt of energy that Earth gets, Mars gets about 0.43. All right, let me ask you one question about volcanoes and then we'll dismiss. Get thy clicker ready. I'm a little bit behind where I want it to be, but that's all right. We got plenty to talk about. Clicker. Volcano. Question number uno. Volcanoes on Earth pour out lots of molten lava, also known as A, B, C, or D. Go ahead and vote. And hey, you guys, I have some. Do not leave. Do not leave yet. 20 seconds. I got to give you some bad news. It's going to disappoint you. It's going to make you sad. After you turn in your clicker, after you do your click, you're dismissed, and there's no homework tonight. Okay, I'll see you on Thursday. Now you can go. Who's clapping? Take down names. Who's clapping back there? I'm just kidding.
So you got any predictions for Super Bowl this Sunday?
My prediction for the Super Bowl is I believe Denver's going to beat them.
You think Denver's going to beat Carolina?
I do.
Why?
Defense and experience.
You don't think Cam Newton going to come out?
Cam Newton's going to make them work their butt off, and they might. It's not a rock solid prediction.
Right.
Okay, man. Clark. Right. It's not a rock solid prediction, but that's what I predict.
Okay.
I mean, it could go the other way, but
I'm
because
from
defense.
Carolina, so I hope they
Okay, it'll be nice if they win. I got to admit that, but defense. Just look how they shut down. No, I'm talking about Denver. They shut down the Cheatriots.
The Cheatriots.
And remember, in the beginning of the year, the Cheatriots were scoring like 50 points a game, except they didn't last week. Yeah, but they had all their guys back. They had Amendola. They had Edel. Yeah, their offensive line sucks. That was the big factor, but they couldn't do jack. So I predict Denver, but I understand that it might go the other way.
Are you rooting for Denver? Or are you just
Yeah, I'm rooting for Denver.
Oh, okay.
Yeah. I like those guys, Von Miller and DeMarcus Ware, and all those guys tearing everybody apart.
Oh, yeah.
They were making Brady look like a chump. So.
Yeah.
Could we build a synthetic atmosphere
In Mars?
on Mars?
Yeah, in the movies.
Will we like control weather instead of the government does that? I know they do.
On Earth?
Yeah.
Yeah. Yeah, they do. The government controls that. Oh, and by the way, I have a bridge that I want to sell you. It's up in Brooklyn, New York. Have you heard of it? The Brooklyn Bridge? It's for sale now.
Oh yeah.
Yeah, just give me all your money and I'll give it to you. I'll let you have the deed to the Brooklyn Bridge.
Okay.
That's how much I believe in weather control. There's no way the government controls weather. I may as well believe in the Brooklyn Bridge. Selling the Brooklyn Bridge.
And the science, or the astronomy club.
Dude, you caught me napping again. It's going to be Wednesday. Robinson Do you know where the Robinson Observatory is? It's